No, no secrets yet. Hopefully everybody had a somewhat productive spring break. Um, I don't know how you could do that, Shelby. That really sucks. Having to move. Sorry. But it happens. Okay, let's see what everyone else has been doing. Puzzles, awesome. Okay. Cool. Okay, so last time you guys had an exam. Looks like most people did pretty well on it, so congratulations, everyone. So I'm glad that at least so far things are working out. So we'll just keep on going. So let's see. Last time we talked about naming, right? We finished all those different compounds and how we could name them. We remembered that sometimes we would have compounds like this. Oh no, am I muted? Okay, so let's see, Arpin, maybe you've got the deafen thing on. Okay, well, so anyway, so we saw that there were some compounds like this. You remember sodium chloride here, our good buddy. And this was ionic, right? This was made of ions. There were positive or negative ions. Or rather, it's both, right? You can't just have them by itself. Okay, awesome, Orpin. I'm glad to see that worked. Cool. So, however, we saw that if we have something like this is not ionic. And we're going to say, therefore, this is not made of ions. Cool. Great, great, great. So, how the heck does this work? Let's consider that instead, nonmetals, they share electrons with other nonmetals. Sharing electrons, yes. So we're going to be able to display that. So let's just look at what we're going to be looking at right now. Let's take we're going to look at methane, right? We're going to see how that carbon is sharing electrons with all of those hydrogens. Do we remember kind of that magic number of valence electrons that all the elements kind of want to get? Someone go ahead, type it out if you remember. Not 7. Very close indeed. Everyone wants 8. Right, so most elements want 8 electrons. Okay, there's a couple exceptions. For example, hydrogen just wants 2 electrons. Remember, since it only has the 1s shell, it can only hold 2 electrons, so there's no way it could get 8. So 2 is just fine for hydrogen. Okay, so consider if we have 1 carbon and 4 hydrogens, how many valence electrons do we have? Between that carbon and 4 hydrogens. bust out your periodic tables. Yeah, so it's going to be 8 again, right? We know that carbon and hydrogen, carbon has 4, right? This will be Lewis structures, like this, Shalia. Okie doke. So we know that each hydrogen has 1, and we have 4 of them. Oops, that does not equal 4. That equals 8 total valence electrons. Alrighty, so we want to figure out how we're going to make it so that that carbon and those hydrogens can share all of those so that all of them will be happy. So what we want to do is typically the first atom that you see in a compound, most often that's going to be the central atom. Okay, so in the center, and then other stuff, let's do purple, is going to be outside. Sure, so typically in a molecular compound, the first element that you see will be the central element. So in this case, carbon is going to be in the middle. Okay, so how we're going to do this is we're going to draw our carbon, since we know it's in the middle, and we know we have 4 hydrogens, so I'm just going to draw them kind of just around that carbon. Alrighty, and so we have 8 electrons to work with. Okay, and so we're gonna want to be able to place these electrons wisely, such that all elements will either have 8 electrons, or those ones that are exceptions like hydrogen will have their 2 electrons. And so anytime we're going to be sharing electrons, we're going to have to share 2 at a time. Okay, electrons are always shared as a pair. They're never shared singly. Okay, so let me just write that there. Electrons shared always in pairs. Okay, so they're never shared, they don't share 1 electron, they'll share 2. Okay, so can we think of a way that this hydrogen on the left here can share electrons with that carbon so that if we draw them, we can see that that hydrogen will share 2 electrons with that carbon. If we remembered, we had 8 total valence electrons to start with, and now we've used 2 of them. Okay, just putting that, sharing them between that hydrogen and that carbon. If you see, we have 6 left, which is 3 more pairs, right? And so we're going to want to just put those around like so. We'll talk about how to do these. That's what today's lesson will be on. And we're going to display it so we can see which pairs of electrons are being shared between which atoms. Now typically, we'll redraw this with just single lines connecting them. And we're going to see that, oops, did not change the color, that this thing is 2 electrons. Okay, that line in between 2 elements represents 2 electrons. So if we see, we can see that this carbon has 4 of those little lines, which branch out to the hydrogens. And so since each of those is 2 electrons, that carbon effectively has 8 electrons. 2 per each line. And we can see also that since each hydrogen has one line on it, that means each hydrogen has 2 electrons, and as a result, the hydrogens are happy as well. So, in this case, all of our atoms are happy. Okay? Let's go ahead and do another one, and then we'll talk about how you guys are going to start doing these. Okay, this is ammonia. Let's see how many valence electrons we have. We've got nitrogen plus 3 hydrogens, right? How many valence does nitrogen have? And then we're going to see that hydrogen again has 1. So, look, magically we have 8 once again. Alrighty, so let's go ahead and draw our nitrogen and some hydrogens around it. And we're going to see the first thing we're always going to do is that everything has to connect to the central atom. That's the whole point of doing these. And so let's just go ahead and start by connecting all of our outer atoms to that middle atom. And so we can see here that the hydrogen on the left, the hydrogen on the bottom, and the hydrogen on the right, they all have 2 electrons. But this nitrogen in the middle only has 6. However, we remember that we have 8 total valence electrons. And so we've only used 6. And so now, because nitrogen is the only atom that has not got 8, or 2 for hydrogen, we're just going to go ahead and give those extra electrons to nitrogen. I'm going to do them in purple, just so that they're different. So remember, we had 8 valence electrons total. We used 6 of them to connect the hydrogens onto the nitrogen, and we had 2 left over, so we went ahead and gave those to nitrogen. As a result, nitrogen is going to have 8, and it will be happy. All right, we have a special name for that. That is what's called a lone pair. Okay, whereas our blue ones were shared electrons. We're going to see, Arpin, typically, yes, but Arpin, we're going to see that when we have, very often you're going to have more than 8 valence electrons, and I don't want to say anything right away to answer that question, Arpin. So we'll get to that in a second. Okay, but so far, is this all right? Yes, Rob, for this class, having more than 8 is not allowed. Okay, in 101, you will see that some of these will be able to go through more than 8. But for now, for Chem 110, we are just going to pretend that 8 is our limit. Okay, just to make it easier on you guys. Alrighty. How about... how about this one? What's the name of this, by the way? You thought you were done with naming? I think not. Very good. So that is indeed phosphorus trichloride. Very nice, guys. Cool. So we want to see our valence electrons. we're going to want to see how many valence electrons phosphorus has and how many chlorine has. Seven for P, not quite. Not quite 6 either. 5, yes. Just keep guessing until you get it right. That's how we solve these. Let's see, I think I've still got my periodic table from like pre-spring break here. It's kind of destroyed. But let's see, where is phosphorus on this thing? So remember group 15, where phosphorus is? Group 15 will have 5 valence electrons. Remember, we were counting that earlier. And then, yes, you guys are correct that chlorine has 7. And so overall we have, fast maths, 26. Alrighty, so we're upping the stakes here. Since, again, phosphorus is written first, we're going to want to put phosphorus in the middle and the chlorines on the outside. The first thing we're always going to do is we are going to make those bonds between our central atom and our outside atoms. All right? So we're always going to start by doing that. If we see here, how many electrons have we now used? Yeah, we've used 6. So we have 20 electrons left. So let's look at these. Chlorine has 2 electrons right now. I'm just, for example, looking at the one on the left. Chlorine has 2 electrons, and it wants to have 8. Right? Only hydrogen wants to have 2. All right, the rest of the things want 8. So, if we want to give chlorine some more electrons, we have 20 left. Let's go ahead and give chlorine what it wants. So let's go ahead and put 6 more electrons onto chlorine. Alrighty. We now have 14 left. If we keep going, this chlorine at the bottom also could use 6 more, as could the chlorine on the right. And if we see, I just used 12 more electrons. Okay, yes, Rob? Yeah, purple and blue right now, I'm just distinguishing between lone pairs and shared electrons. So since we have those last 2 electrons, yeah, the ones that are in between 2 atoms are going to be shared. Okay, so those last 2 electrons we'll give to phosphorus, because phosphorus is the only one that does not have 8. All right, and then so you see we will now have used all of our electrons and everything is happy. Okay, so typically yeah, in this case, yes, it works nicely. We've just evenly divided them up between all of the atoms. So it works out nicely. When we draw these, though, we typically don't have so many dots lying around. It's typically easier if you just draw the shared ones as those lines. Okay, but you still have to put on your lone pairs. We're going to see a little bit later that these lone pairs are going to be very important for us. Okay, so far so good. Cool. Alrighty, let's up the ante a little bit more. So, how about this one? Carbon dioxide, our favorite molecular compound. Carbon in the middle, oxygens on the outside. Oh, I forgot our electron count. We have 4 for carbon, plus 6 for each oxygen. Very nice. So that's going to be 16. Yes. No. Yes, 16. The math is difficult. Okay, first thing, always do a pair of electrons in between the central atom and the outer atoms. So how many have we used now? Let's make that a little better. We've used 4, right. So we have 12 left. The next thing we're going to want to do is go to those outer atoms and see if we can't give them enough electrons so they could get to 8. Alrighty, so how many more electrons will the oxygen need to get to 8? 6, right. So, boom, 6 electrons there. Very good. And another 6 electrons there. We have just used 12. Uh-oh. That poor carbon in the middle is just so sad. It only has 4 electrons. But the oxygens all have 8. So the oxygens are happy, but carbon is not. And so, what happens now is in order to try and make that carbon happy, we're going to end up sharing more electrons. Instead of having 3 lone pairs on each of those oxygens, they're going to end up sharing them with carbon. And so we're going to see that now we're going to have, yes, Manuel, we're going to have that. We're going to have now 2 pairs of electrons shared between each oxygen and the carbon. And we're still going to have 2 more lone pairs on the oxygens. Okay, we took 1 lone pair from each oxygen, and we put those in the middle to share with carbon. And so, as a result, the structure that we get will look like this. Carbon dioxide. Oh dear. Try again, Manuel. Nope, and kidding has 2 D's. Caliph. Yes, very good. Indeed, the writing does not help. So, when we share 2 pairs of electrons, we are going to call that a double bond. Everything that we've had so far is a single bond. All right, however, in the carbons now, we have double bonds. By the way, these bonds are specifically called covalent bonds. All right, we remember co kind of means like together, right? And valent obviously means valence electrons. So by putting these valence electrons together, we call them covalent bonds. They're shared electrons. So that carbon in carbon dioxide is sharing all of its electrons with the oxygens, and the oxygens have a few left to themselves. Okay, so the oxygens are sharing. So are single bonds, Elsa. All the stuff that we're going to talk about today are covalent bonds. Previously, we've talked about ionic bonds, which are the positive and negative that are just kind of stuck together because they attract each other. But covalent ones are going to be all these non-metal compounds. Okay? So both double, single, and as we'll see, triple bonds will all be example of covalent bonds. Okay? Let's do another one, and then we'll kind of see how this is done, and then I'll let you do some examples. Let's see nitrogen. All right, guess which one of these is the central atom? This is big brain time. Yay! Yeah, there's not really one, but whatever. Cool. 2 nitrogens. Okay, how many valence electrons do we have? Yes, you've got 5 times 2, which is 10. First thing we do, bond in the middle. We have used 2. We have 8 left. So, let's just give some arbitrarily around. We can do this, for example. Oh no, we're out of electrons. So, I have no electrons left. I would like to keep putting more on nitrogen on the right, but not going to happen. We don't have any more. So we see the nitrogen on the left has 8 electrons. It's happy. But the nitrogen on the right only has 4. And so, yeah, exactly. We're going to go ahead and share even more. If we did this, just put one more pair in, that nitrogen would have 6 on the right. But if we put 2 lone pairs in, now we're going to be able to have a triple bond. And so that drawn out, three bonds, and the lone pairs on the outside. Yes, Robert, nitrogen is in group 15. Everything in group 15 has 5 valence electrons. Remember, if the group number is more than 10, just subtract 10 from it, and that's how many valence electrons it has. So group 13 has 3, group 14 has 4, 15 5, 16 6, etc. Cool. Okay, and then so we will draw this like this way. Group 10 is part of transition metals, Robert, so we're not going to mess with those. So group 1 has 1, group 2 has 2, group 13 has 3, group 14 4, etc. Okie dokie. So this is called a triple bond. All right, we're sharing 3 pairs of electrons between those. The pics on the side. What pictures? New update? How exciting. Student profile pictures. Awesome. Well, who knows? Okay, cool. So, let's just kind of summarize our things here. The first thing we do is count all valence electrons. Oh, that's pretty cool. So you guys are all there hanging around on the side. Oh well, cool. Second thing we want to do is arrange outer atoms around the central atom. Then we're going to make, or let me just say it. Whoops. Come on, there we go. Add one pair between each outer to the central atom. How interesting. So, it could be so, I did recently just do Discord Nitro, just to make the resolution a little bit better for you guys. So maybe this is a function of like the more, the fancier one. So I paid money for you guys. You should be really, appreciative. No. Okay, cool. And then the last step we have, or rather second to last step, we add lone pairs to outer atoms. Then add lone pairs to the central atom. This is until 8, by the way. Remember, 8 is that magic number. And then the last one is we make double or triple bonds another way of saying that is not enough on the central atom. Okay, I realize I've gone a little bit over what one thing could show, alas. But hopefully we know to count the atoms or electrons to start with. Alrighty. So this is just kind of a little step-by-step thing to what we've done so far. Alright, do we have any questions on any of these steps? Remember, the first one is just counting valence electrons. Alrighty, Marissa's typing. I will wait to see what she says, and then I will make one adjustment to this. Kind of, Marissa. It depends how you want to define priority. We do want to give electrons to the outer atoms first, and then afterwards we want to give them to the central atom. And if we run out, that's when we're going to make double or triple bonds. So we never want to start off with double or triple bonds. We only want to do them if necessary. So that, and the if necessary is if there's not enough on the central atom. Yeah, yeah. So again, it is semantics. It's much, much more common to see the ones with the lines, Robert. That's just very much convention. If you go to Wikipedia and look up any of these thingies, you're going to see the lines, not the dots. Okay. Yes, Zoe, this is the Lewis method. We're making what are called Lewis structures. Sometimes, Marissa. For example, these, the nitrogens here have one lone pair each. So it's an odd number of lone pairs. In this case, each oxygen had two lone pairs. That's an even number. However, they all must be pairs. Yeah, you're never going to have single electrons. I think that's more your question. Yeah. So there will always be an even number of electrons on the outside. Yeah. If you have one by itself, there are a few molecules that have that. Those are called free radicals. Those are not good. They're highly reactive. They destroy things. So obviously, blah, blah, blah. They're just normal electrons. That's it. Yeah, lone pairs are just electrons. Yeah. No difference. Okay, I have now 1. You see I've left a little bit of space between 1 and 2. Aha, you thought you were done. Yes. Alrighty. So, we're never done. If we have something that is charged, we will adjust our number of electrons by that charge. Okay, remember, for something to be negative, it means it has extra electrons. And for something to be positive, it has reduced number of electrons. Alrighty, so let's go ahead and take a look at some examples using this charge thing. You're going to see that in 101, Robert, so I will just leave that as that. Let me adjust that. What's the name? Very good. So we have S plus 4 oxygens plus 2 electrons, which is 6 plus 4 times 6 plus 2, which is 32 electrons. Notice, green, that this -2 charge, correct, Robert, yeah, if something were positive, you would get rid of some electrons. Okay, so that 2- charge has added 2 extra electrons to our ion. Okay, so that's how that adjustment step works. Alrighty, so next thing we want to do is we want to arrange the outer atoms around the central. So central atom goes in, 4 oxygens around it. Now we want to add 1 pair between each outer atom and the central atom. Since I've been doing those in blue, I will do them in blue. And remember, you always want to keep track of how many electrons you've used, okay? So we've used that many, 8. So we have 24 left. Next step, we are going to add lone pairs to the outer atoms until they reach 8. Alrighty, so each of these oxygens needs 6, right? 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. That's 12 so far. Now I've used 18. Whoops. And now I've used 24. Let's just go ahead and now check all of our atoms. All of these oxygens have 2, 4, 6, 8 electrons around them. And that sulfur in the middle also has 8 electrons. So all of these atoms are happy. We're done with our structure. So, as always, we're going to redraw it with the lines. And then we must put in our thousands of lone pairs. Yes, so single bonds are just lines, and that's one pair of electrons. All right, we have one last step. Because this is an ion, we just have to indicate that it is charged. Okay, and we do that by putting brackets around it as well as the charge. Okay, so anytime you have an ion, that means something that's charged, you're going to put little brackets around it as well as the charge of that. Okay, so 7 brackets if charged. Okay, any questions on sulfate? Alrighty. I am going to give you four of them to do yourself. One special thing. That one's just a bit of a exception. But I've indicated that it is the central atom in that case. Okay, how about we also do... what are some good ones? Ooh, how about this? Oops, oh well. That is a +1. Yeah, that is the ammonium ion. And then, how about one more? Let's do... Oh, you know what? Oh, whatever. We'll just keep it that way. It sounds like we may have a visitor. Let's go check. Hello there. Any guesses who it is? You're right, it is indeed Gumbo. Now, creature, you would hear something. So Gumbo has come along looking for food. Yep, very good. Bonus points. Yes, Gumbo, I know. He has no teeth. Good boy, Gumbo. Okay, off you go. So he'll scrounge around for a bit. Okay, so I want you guys to... Let's see. That's exactly what Gumbo would do. Okay, so do these 4 on your own, and I will put up the answers, and then we'll take our break. And more importantly, someone has put... We will do cookie blob for that one. Six plus 6 plus 6 plus 6. Yeah, you're right, Robert. Though I think you mean SO3, 2 minus. But yeah, 26. If you have extra electrons, so remember we always want to kind of follow the thing, so you can definitely have that happen if you have enough electrons. Okay? As we look at number 5. Okay, so I'm going to just do the first one. You should end up with this. Ah, it's not quite 9, is it? That's 5. It's 8. Remember, because it's positive. Green. Positive means we subtract 1. Ah, okay, got it. Let's make that a little bit nicer. So in another, oh, hi, Oz. Come on, little Oz. Nope, doesn't want to come in. Okay. Sad. Dividing the electrons. So Robert, just by putting in the single bonds, you are going to use up all your electrons. But we can go over that one in a little bit, yeah. Oops. So that is what you should get for hydrohydroxic acid. There's not going to be any double bonds in water because hydrogens only need 2 electrons. So remember that we don't have to give any electrons to the hydrogens after that because they're already happy with their single bond. Does that make sense, Elsa? Yeah. So remember, hydrogen only needs 2. Cool. That was just my choice, Samble. No real, yeah. Again, Marissa, that would be something we'll cover later. So right now, just do it however you want. If you want to put the electrons on top and bottom, do it a straight line, that is totally fine. Oh yes, angles matter. Oh, that's ugly. Very good. Let me just make this a little bit separated. So Tiffany, hydrogen only needs 2 electrons to be happy. It's not going to get any more than 2. So we're never going to see a double bond with hydrogen. It doesn't matter, Marissa. You can do it either way. In fact, in this next one, I will do it the opposite way. My eyes. Your eyes. Let's see, maybe I have a treat around here. Yes, I do. Come here, eyes. Yes. Up we go. So here's Oz. Oz's Gumbo's dad. Old Man Oz. It's very often they're just dots. So you don't typically have them as open circles, Rob. They're just dots. I mean, again, that would kind of be stylistic choice, but again, you're going to usually see them filled in. This one is my favorite. So old. Oh, they all know. Creature used to be my favorite, but this guy took over. He wants to go in his bed now. Okay, go on. All dogs are sweeter than Creature. It's not a, you know. Alrighty, so when we come back from our break, we can talk about these if anyone has questions on any of them. So yeah, go ahead. We'll take our break about 10 minutes to 4:40. We'll be back, and we will continue.